Hello. Now we will study the effect of heat on solids, and the solid we will take as volumetric thing. So here we are having a sphere of radius r1. When the temperature was T1, this radius is r1 when it's a natural radius basically, when there is no strain inside. So we increase the temperature from T1 to T2, so this solid will become bigger and its radius is becoming r2. Okay. So this was the initial volume and this is the final volume of this solid. So we want to check corresponding to the temperature change how the volume is changing, and obviously this is also an empirical result. We perform the experiment with lot of spheres, lot of solids, volumetric solids, and after performing those experiments we come across that any fractional volume change is proportional to the temperature change. So fractional volume change, that is V2 minus V1 upon V1, that's a fractional volume change, it was proportional to temperature change for each and every material we come across. Okay, that was a relationship, and for that the condition was that temperature change should not be large. For small temperature change, this relationship was valid for small temperature differences. So there was this proportionality sign which was coming for every material. So we remove this proportionality sign, we introduce a constant there. So V2 minus V1 upon V1 becomes gamma times of T2 minus T1. That becomes a formula, where this gamma is a coefficient of volumetric expansion. This is coefficient of volumetric expansion. Okay, this is a constant which depends upon the material you are using for this solid. If we rearrange this equation gets converted into V2 is equals to V1 1 plus gamma times of T2 minus T1. That's the final equation, where gamma is coefficient of volumetric expansion, and from this relationship you can calculate any volume for any material, not just for a spherical surface. You can calculate the volume of any material, any shape of material. Okay. So if we are having spherical, which is symmetric actually, in that case we have an added advantage. We can convert the volume in terms of radius which is linear dimension. So what we do, we want to make the relationship here also between the gamma and alpha. So if this material is homogeneous, so for homogeneous and symmetric, obviously it has to be symmetric also, otherwise we'll not be able to make the relationship. If this material is homogeneous as well as the dimension is symmetric, in that case we can write V1 is equals to 4 by 3 pi R1 cube, as well as V2 is 4 by 3 pi R2 cube. If we replace the values, this 4 by 3 pi will cancel out. So we'll have the relationship R2 cube is equals to R1 cube 1 plus gamma times of T2 minus T1. That is our equation 1. So this R1 is one dimension. So if in this solid, if this solid sphere, for this solid sphere, if I apply the linear expansion formula, if we apply formula for linear expansion for sphere, solid sphere, in that case R2 will be equals to R1 1 plus alpha times of T2 minus T1. Here we are assuming this is homogeneous as well as this is symmetric also. So if this will be the relationship between the radiuses, and for all radiuses, because this system is symmetric as well as homogeneous, so radius, as you change the radius, materials property are going to remain same. So from equation 1, we put this value in equation 1, we'll have R1 cube 1 plus alpha times of T2 minus T1 is equals to R1 cube 1 plus gamma times of T2 minus T1. This R1 and R1 will cancel out, and there is a cube also. Now you can see, just like the previous case, this value alpha T2 minus T1, this value is very small compared to 1 for small changes, and alpha is also very, very small. So we can apply the binomial expansion. So from binomial expansion, we can convert this equation into 1 plus 3 times of alpha T2 minus T1. that will be equals to 1 plus gamma times of T2 minus T1. And upon rearranging, we will be getting gamma is equals to 3 alpha. So this is the relationship between the coefficient of volume expansion and the coefficient of linear expansion when material is homogeneous as well as symmetric. So if you remember earlier when we were dealing with aerial objects, we got the relationship as beta is equals to 2 alpha. So if you combine these two relationships, we get alpha is to beta is to gamma is equals to 1 is to 2 is to 3. So that's the relationship between the coefficient of linear as well as aerial and volumetric expansion when the material is homogeneous as well as symmetric. So when the material is homogeneous as well as symmetric, for that material, it's up to you to utilize the linear expansion formula or aerial expansion formula or volumetric expansion formula. All formulas will be valid. But if it is not homogeneous or symmetric, in that case we can apply the formula corresponding to whether it is a volumetric object or area object or linear object. We cannot interchange the formulas. Okay. Thank you.